In 2009, a group of neuroscientists did something absurd. They put a dead salmon, yes, a literal dead fish, into a brain scanner. Then they showed it photos of people in emotional situations and asked it to judge their feelings. And the standard analysis of the day lit up. It reported brain regions in the dead salmon that were significantly predicting human emotions. Obviously, the dead fish wasn't reading minds. It was a statistical mistake, failing to correct for thousands of simultaneous comparisons. Run enough tests, and pure noise will throw up something that looks significant. That embarrassing salmon became a famous warning sign for a whole field. This paper argues that AI interpretability is now having its own dead salmon moment. Here's the alarming part. The tools we use to peek inside AI models, feature attribution, probing, sparse autoencoders, even careful causal analyses, can produce confident, plausible-looking explanations for a neural network whose weights are completely random. They explain models that compute nothing. These are the dead salmons of AI. The authors show this with a minimal example, and it's chilling. They take a BERT model with totally random weights, it has learned nothing, and feed it movie reviews. Look at Figure 1. On the left, several internal directions appear strongly correlated with the sentiment of the review. On the right, a simple probe reads sentiment out of this random network with real accuracy, from pure noise. And this isn't a niche curiosity. Interpretability is supposed to be how we make AI transparent and accountable, especially as these systems move into medicine, hiring, and the law. If our tools hand us confident explanations for models that aren't even thinking, how can we trust them on the models that are? The dead salmon is just the most dramatic symptom. The paper documents a whole pattern of statistical fragility across interpretability. Tiny changes to the input can flip an explanation. A different random seed gives a different story. Explanations rarely generalize. And often, several incompatible explanations all fit the same behavior equally well. So what's the common root cause? The paper's central diagnosis is a single, powerful idea, non-identifiability. Informally, a question is identifiable if the data can pin down one unique answer. Most interpretability questions are not identifiable. The model's traces simply don't determine a unique explanation. Many explanations fit equally well, so the method just picks one, almost arbitrarily. Non-identifiability shows up in two flavors. Underspecification. When you only look at inputs and outputs, many different internal stories explain the same behavior. And overdetermination. Real networks are full of redundant, parallel pathways, so many different mechanisms are each independently enough to cause the behavior. Either way, the truth isn't unique. Overdetermination has a great name in the literature, the hydra effect. Find a component that looks causally crucial, you ablate it, and the behavior survives because a backup pathway quietly takes over. Cut off one head, another grows. So this component is the mechanism is exactly the kind of claim the data can't actually pin down. So what do we do about it? The paper's core proposal is a reframing. Stop treating interpretability as a quest to read off the one true explanation and start treating it as what it really is, a problem of statistical and causal inference. Let's unpack what that means. There's an immediate, practical fix for the salmon itself. Whenever you analyze a trained model, run the exact same analysis on a randomized version and test against that. It's a null hypothesis of random computation. If your trained model doesn't beat the dead salmon, your finding is noise. The paper shows this alone removes many false discoveries. But the deeper fix needs structure. First, view the network itself as a structural causal model, shown in Figure 2. The internal activations are variables, the input distribution is the behavior you want to explain, and the layers are the causal mechanisms. Now you can ask precise causal questions, like what happens if I force this activation to a value, and you can intervene to answer them. Second, treat an explanation as a surrogate model, a simpler stand-in that tries to answer those causal questions about the big network. Think of interpretability as compression. Find the simplest description that still answers the questions you actually care about. An explanation is good only insofar as it predicts and supports manipulation. And this gives the key payoff, captured in Figure 3. Every interpretability method is really three explicit choices. Mu, which causal questions you want answered. The surrogate class, what form the explanation can take, a circuit, a probe, a concept vector. A discrepancy measure, how you score whether the surrogate got the answers right. Name all three, and you've defined a real, testable task. Once those three choices are fixed, finding the best explanation becomes an honest estimation problem, just like fitting any statistical model. And crucially, you can now ask whether the task is identifiable. Does it even have a unique best answer? The paper's analysis says most popular interpretability tasks, as currently posed, do not. Here's the most important consequence. If interpretability is statistical inference, then like any science, it must report uncertainty. You'd never trust a drug trial that reported an effect with no confidence interval. You shouldn't trust an interpretability claim with no error bars either. When an explanation is non-identifiable, that uncertainty is simply large, and honestly saying so is the point. This reframing also dissolves an old fight. There's no single true explanation of a network, and that's fine. Different goals, just describing, predicting, or controlling, call for different questions. But once you fix your goal, the three choices, the best explanation becomes an objective fact about the system. Freedom in goals, rigor in claims. And it opens a clear road forward, borrowing tools that rescued other fields. Characterize which interpretability tasks are even identifiable. Use Bayesian methods that naturally express uncertainty. And build a cumulative science with pre-registration, shared traces, and meta-analysis. Exactly the reforms that pulled psychology and neuroscience out of their own replication crises. Why does this matter so much? Because we're increasingly using interpretability to certify that AI systems are safe, fair, and doing what we think. If those explanations are dead salmons, confident but spurious, we get a dangerous illusion of understanding. Putting interpretability on a real statistical footing is how we earn genuine trust instead of faking it. The authors are appropriately humble. This is a position paper, not a finished theory. Their proposed framework is one formalization among many, offered as a starting point, not a final answer. The core methodological demand is hard to argue with. Make your assumptions explicit and quantify your uncertainty. So here's the one-line takeaway. The fact that our tools can explain a dead salmon or a random neural network is telling us something deep. Most interpretability questions don't have a single, well-defined answer yet. Treat them as statistical inference. Name your assumptions, report your uncertainty, and interpretability can grow into a real, rigorous science. Thanks for watching.